element. With that, I'll pass the mic to Puneet.
Thanks a lot for the introduction. Yeah, so my name is Puneet, and today I'll be talking about something that was fascinating for me as I was trying to research for this presentation. So I'll be talking about the pattern evolution in biological systems. So basically, the reaction diffusion mechanism was shown to explain the different pattern evolutions in living organisms. So different patterns, hair follicle density, tooth formation, digit formations were all explained by the reaction diffusion mechanism. And this idea was first put forward by Alan Turing in 1952. And recently he was documented in this movie Imitation Game as well. So basically, unlike in the previous examples that we've seen where we had just one species diffusing into the other, here we have two species which are interdiffusing into one another. So basically, the two diffusing species here are A and B, A being the activator species and the B being the inhibitor species. So A basically is a self-catalytic species which increases the reaction rate of A as well as B, whereas B is the inhibitor species which inhibits the reaction of both A and B. So what basically happens here is that there's a slight kink in the concentration of the activator species. And this, as you might expect, this starts off a chain reaction which basically increases the reaction rate of both A and B, and this kind of leads to the formation of reaction cores which have like increased concentration of A and B. But the important thing to note here is that the diffusivity of B is higher than that of A. So what that basically means is that as the reaction keeps going ahead, after a certain time and at a certain distance, you might expect the concentration of the inhibitor to start dominating over the concentration of the activator species. So what happens is that it starts forming reaction cores, and these cores basically cut off these reaction core regions. And as a result of that, they start forming these so-called waves, periodic patterns. And these waves are what are known as Turing waves. And we have a small simulation of how these patterns come to evolve. And so basically, this kind of model was used to explain a lot of different features in biological systems. Here we have an example of an anglerfish. And as you can see, there's a simulation results from using this kind of models. So basic setup for this is this kind of equation where we have the fixed second law and with an extra reaction term to it. So the perturbations in the system basically come up from the statistical variations. And so the production of activator and inhibitor species have different form of interactions which basically determine the kind of patterns that get generated. So if there are cubic interactions, we get stripe formations, and for quadratic interactions, we get circular patterns. So as we have seen that there are several mechanisms which can be explained through the reaction diffusion system. So I believe that there'll be many more phenomenon in the future that may be explained by such reaction diffusion mechanisms. So with that, I'd like to end the presentation. If there are any questions.
Yeah, one question is, what are the axes on your Turing waves?
Oh.
Because it's this thing hanging in
space.
It's
just the distance and the concentration.
Distance, concentration,
yeah.
Okay,
yeah. Yeah, he had a, huh?
I just want to know, like, so you have like an activator that activates both things, and you have an inhibitor that inhibits both things.
Yeah.
Does that mean that they're like when the inhibitor is greater than the activator, there's basically just like one color that the fish normally has or something?
No. So the inhibitor is basically restricting the formation. So it's not just these the concentration cores that you get, they get there'll be other functional molecules that come. So if a color chromophore comes and attaches to that reaction core that I mentioned, like the peaks here, So at these regions, the pattern will be the most strongest. So the colors will basically form there, and then you won't have any colors in the regions where there's the dip in the concentration. So that is basically how the patterns get generated.
So where are the fish exactly at speed? Like, can you like point them out?
Oh, sorry.
Like the fish.
Oh. Yeah. So basically. So this might be like one pattern, and like basically the different colors is like different regions. I mean, I'm not really sure where exactly that ends and where the other thing begins, but that's how basically the patterns get formed. So.
So it's interesting from concept. I'm not familiar with this field at all. The one thing I struggle with automatically is the dimension of the structure, because you have cellular levels and cells are smaller. Why would such a diffusion reaction mechanism go beyond cell walls and everything?
No, so these basically start at the embryonic stage. So this is when the fish is really small. So that's when these patterns. So basically what I read is that, so it's like when the embryo is just beginning to develop, these kind of interactions happen at that stage, and then as it grows on, there's different interaction with chromophores and things like that, which leads to So this is not. I mean, but this mechanism still continues. So like they also said that so for many animals, basically like cheetah or something, so the growth of these patterns basically ends after a certain stage. I mean, like. So I mean, like, if the cubs of leopards they have straight patterns, and then they gradually go to circular patterns. So that is basically the ending of if the pattern is just constant, and that's how they tag animals as well. So but in case of fishes, they say that the pattern keeps happening throughout their lifetime. So that's why they most of these examples they usually use. The example for an anglerfish, so they basically have the pattern generation going on through the lifetime. So,
did anyone ever try injecting inhibitors and others to modify concentrations and get different patterns?
They have, I mean, they just. I mean, this is just one example. They tried to simulate different patterns.
Yeah, simulation, but in real, they're taking fish and injecting the chemicals and see.
They did. They didn't do that exactly, but they checked it for some mutations in the animals, and so they checked the difference in. So that's how they. So I mean, they didn't actually go and inject inhibitors and things like that.
When you see people pay a lot of money when you get dogs like Dalmatians with certain spots. And so
I don't know. I mean, I don't know if it's ethical or I don't know what.
Yeah, I don't know either. But usually people do a lot of crazy things. People are trying now a head transplant of a human. So
it's a question.
So can you take has anybody ever took these patterns on these fish and backed out what occurred when it was born, to try to determine different things in the water or something?
I mean, some of these patterns were formed as a result of their interactions with the flow stream and things like that. So I mean, they do have this.
So the knowing of the flow stream and then observing the patterns, has anybody tried to reverse?
I'm not sure. I didn't really do so much research into that, but there might be.
So this seems really interesting.
That's what I mean, I was trying to do doping in semiconductors first, but then I come across this, so I'm like, I have to present this. So
I really appreciate it. It's really nice. Thanks. Any other questions? No? Okay, thanks.
Thanks.
So it's just time to jump into did you turn it off? So the next